All right, we'll take a look at unsupervised learning. We'll look at some clustering. Just we'll start with like just basic clustering, and then we'll also look at principal components analysis. And these both fall under this category of unsupervised learning. Okay, and so kind of the pretty much everything we've done so far has been supervised learning. Okay, and when you do supervised learning, you have some input values, your x's, and you try to get them to match the output values. Like you know the answers that you want, and you're trying to get your results to match that, right? So the neural network, we knew that this digit should be a 6, and we tried to get the inputs to come out and say it's a 6, okay? Or whatever things like you're doing in your homework, you're like trying to identify the species of flower, right, based on the petal length and petal width and stuff like that. And so you have input values and you have the output value. You know that it's supposed to say setosa or supposed to say virginica, and so you're trying to get your results to match that. So that's supervised learning. You know what the answer should be, and you have a way to measure how different your prediction is from the correct answer. Okay, and so we say that's your measure of loss, measure of how wrong you are. Okay, today or this week's stuff, or I don't know, today, Friday, whatever we want to call it, it's unsupervised. Okay, there's no target value. You just have data, right? You've gathered some stuff, and you're trying to identify interesting, we might call this structure. You're trying to find something interesting inside the data. And so so one of these ideas is clustering. Can you identify clusters inside the data? And that's going to be to try to like group similar observations together. And then another is dimension reduction, where you have a bunch of variables and you kind of want to reduce it to a few or something along those lines. Okay. All right, so we'll talk clustering. We'll start off by talking clustering, and we can get really into clustering. I don't know. I'm going to try to devote half, maybe some of our time to clustering, some of our time to PCA. There's a lot you can talk about in unsupervised learning, but we'll see what we do. Okay, so the big idea is we want to create groupings of objects so that the stuff in a group are similar to each other, and when you have different groups, they are not similar, right? And there's all sorts of ways to define similarity and to do the thing. So some applications group similar products together. So that's what Amazon is really good at, right? You buy one thing and then they say, or like you're looking at one product and they say, oh, you know what? Other people also bought this product and this product. Why don't we just add all three of them to your cart at this low price, or, in a similar vein, there's like grouping similar documents and things like that. You're trying to organize your stuff, okay? Or grouping physical locations together. So, Uber and Lyft, they try to, now that they have these pool things, they're trying to figure out like, oh, these people are on the same path and stuff. Okay, so the simplest clustering algorithm that we have is the k-means clustering algorithm, okay? It starts with a K, so it sounds a lot like KNN, okay? But they're totally different, okay? So KNN is supervised classification. You have the answers, you have the classifications, and you look at your observation and you're classifying things, okay? K-means is unsupervised and it's clustering, okay? So they sound similar just because they have a K and you call it K-means, K-N-N, they sound similar, but they're different, right? And so K-means clustering, usually the way we are going to say objects are similar based on their like Euclidean distance, okay? This thing looks crazy, okay? All this is basically saying we're going to have some vector z, or some indicator variable z sub nk, and that just means every observation, if you have n observations, every one of them has a z. Actually, every one of them is going to have k z values. So you have k different clusters. So if we have 3 cluster values, or 3 clusters, if we're looking for 3 clusters, every observation is going to have 3 z sub k values, okay? And it's basically going to be 1 if it's in the cluster, and it's a 0 if it's not in the cluster, okay? So, if I were to draw this, okay, you've got observation 1, 2, 3, 4, and then basically you're going to have a z for cluster 1, a z for cluster 2, and a z for cluster 3, and it's going to be something like 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 0. Okay, each row there's going to be one of these things. This is for 3 clusters. Okay, and each of these things will have this, right? And you might also have an x and a y variable, and you might have, or I should call this x1 and x2 or something, and this might be like 0, 1, and 4, 6, and 5, 5, and -3, -2, or something, okay? And so what this is saying, when we do mu sub k, okay, so if we're going to do like mu for cluster 1, it's basically saying we're going to look at only the ones where the z sub 1 is basically not 0, okay? So it's going to be 4 plus 5 over 2, and then 6 plus 5 over 2, right? So if we take the sum of the z1 column, we're going to get 2. That's what we get on the bottom. This is sum of the z1 column. And then here, if I multiply z1 times our x values, the 0 times the 0s would be 0. 1 times 4 is 4. 1 times 5 is 1. And 0 times -3 is 0. So the other ones go away, and we're basically just adding for the ones where z1 is 1, right? Okay, so that's what we get. So the mean of this data so far is 4.5 and 5.5 or something like that. Okay, and you would do this for all of the clusters. Basically, we're just saying the centroid is the mean of the values that belong in that cluster. Okay, but this is how you would express it, I guess, mathematically. Okay, it's the mean of the values that belong in that cluster, and we're basically just either multiplying it by a 1 or a 0 here. Is that okay? All right. This is the k-means clustering algorithm. Okay, so step 0, you have to decide how many clusters. So what value k you're going to use. Am I looking for 2 clusters, 3 clusters, 4 clusters, or 5 clusters? Okay, this is not easy. This is a tough problem, okay? Because you can always find an excuse to add another cluster. All right, and you know, um, well, I'll let you guess. So how do you think we're going to decide how many clusters we should use? It's the same answer that it's always been. What's that?
Just looking at it.
Looking at it, okay.
You just keep going and adding stuff until it breaks.
No, cross validation. All right, so we're gonna try out this many clusters, and we'll do cross validation, see how many mistakes or not mistakes, but just like, yeah, I'm sorry, sorry, that's not correct. Yeah, we just try K and we see how much improvement we get. I'm sorry. Cross validation is not the right answer. Okay, never mind. I take that back. Yeah, there's no validation to do. Sorry. It's like cross validation is the answer for everything, but I guess it's actually not the case here. All right, sorry, my bad. Rewind. Okay, we're gonna randomly assign. Okay, so the first thing we do, we randomly assign points in your data to each of the clusters. You got 3 clusters. You're gonna randomly assign them to one of the 3. Okay, all of them. You just start off random. And then, once you have everything assigned to a cluster, you're going to calculate the centroid of the values in each cluster. So you're going to say, what's the center of cluster 1, and what's the center of cluster 2, and what's the center of cluster 3. These have been randomly created, all right? So probably they're going to be quite similar, these cluster centroids, but they're also going to be slightly different, okay? And then after you do that, you reassign values to the clusters. And this is the k-means part. So the means is you find the centroid. That's the mean part, okay? And then you reassign the clusters by associating the value in the data to the nearest, probably using Euclidean distance centroid. So you figure out like which centroid, which mean is the closest. And then you just do that over and over and over again. Repeat steps 2 and 3 until you converge. Okay, convergence is when nothing gets reassigned. I think this is going to make the most sense if I just do an actual tiny data set or something. Okay. All right, so here is some pretend toy data. All right, now right now they're all unlabeled. Okay, but we've got the points basically 0, 0, 0, 1, 1, 0, 1, 1. And what is this? This is like 3, 3, 4, 3, 3, 4, and 4, 4. Okay. All right. If you had to cluster these into 2 clusters, it's very easy. Just we would do one down here and one up here. And we'd say these ones are similar and these ones are similar down here. Okay. We can do this visually, right? Okay. How does the k-means algorithm work, all right? So step 1, we got to figure, step 0 is how many clusters are we going to look for? We're going to say, look for 2 clusters, okay? And then, but it's not a trivial thing, right? So, I mean, on this data set, it's obvious, right? But it might not be so obvious. But anyway, you say we're going to look for 2 clusters. And then the next thing we do, the first thing is we just randomly assign all of these points to one of the 2 clusters, okay? So that's what we're going to do, okay? So we're going to say we're going to look for 2 clusters, and I just sample between the values 1 and 2, and I just assign them, okay? And I call these the assignments, and I color these based on the assignments, okay? So after doing random assignments, I got 3 assigned to maybe the black cluster, and I got 5 points assigned to the red cluster, okay? And okay, so this is what we have, and now I'm going to calculate the centroid of each cluster, okay? So we've got this point, this point, and this point is the black cluster, and we're going to find the center of these 3 points, okay? And then we've got these 5 points in red, and we're going to find the center, or the mean, of those 5 points, okay? So here are my things. We have 0, 0, 1, 0, 1, and 3, 3 assigned to cluster 1, okay? So the center of cluster 1 is going to be, we're going to add 0 plus 0 plus 3. Okay, those are the points that belong to cluster 1. And take the mean of those, and we get 1. And then we look at the other variable, x2, and we have 0, 1, and 3. And we take the mean of those 3, and we get 1.33. We do the same with the 5 points in cluster 2. We have a 1, a 3, a 4, and a 4. And I take those, and I get the mean is 2.6. And then for x2, I have a 0, a 1, a 4, a 3, and a 4. And I take the mean of those 5 values, and I get 2.4. Okay, so so that's how I did it, just kind of manually. I can do this using dplyr by just saying group by the assignments and take the mean of x1 and the mean of x2, and it gives me the same 1 and 1.33 and 2.6 and 2.4. All right, is that okay? So far, so good? All right, so this is the centroid of cluster 1. So if you take the average of these 3 black dots, it's right here. And the average of the 5 red dots is right here. Okay, and, and this is a little silly, but we go through every single point and we say, all right, is it closer to this centroid or is it closer to this centroid? Okay, so we're going to start. So I'm going to just start here. So none of these, right now, none of them are assigned. And we're going to say, is this point closer to the black or the red centroid? Okay, it's closer to the black centroid, okay? So it gets assigned to black. This one, is this closer to the black or red? Closer to the black. And this one, closer, which one is closer? The black centroid is closer. And which one is closer? The black centroid is closer there, okay? Now we come over here. Which one's closer? The red centroid is closer. 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 Okay, so these are the assignments. Now, okay, now that we've looked at which centroid is closer, for all 4 points here, this centroid was closer, and for all 4 points here, this centroid was closer. Okay, and now, so that was, we found the centroids, and then we did all of the reassignments. And now we go back and we find the centroids, okay? So we're going to take these 4 points and say, what's the centroid of these 4 points? We're going to take these 4 points, what's the centroid of these 4 points, okay? And it's exactly what you think it is, 0.5, 0.5, 3.5, 3.5, which is right here and right here, all right? And then we can go through and we can say which one is closer, right? And we can say, like, okay, between this centroid and this centroid, and we would see that none of the assignments would flip. Okay, none of the assignments would flip, and so therefore we have converged, and this is how the points should be clustered. Okay, easy? Good. All right. Okay, so here is a little bit more of a mix of data. Okay, so here is, like, I have generated 3 multivariate normal samples of data, okay? And they're kind of mixed, and so according to this, you know, we've got some red dots over here and some green dots mixed in here and whatever, but we're going to perform clustering here, okay? So I guess when we look at it, it's actually we don't know where they're coming from. So they come in, they're totally all seen as all the same color, and we just randomly assign some of these to be black, some to be red, some to be green. Okay, so we're going to have a black cluster, red cluster, and green cluster. Okay, those are just the default colors that R does. Okay, and so so I just randomly did these. Okay, we don't even necessarily have equal counts of these things, right? Just like for the previous problem, 3 ended up in the black and 5 ended up in the red. So I don't know how many are in black and green or red. It doesn't even matter. Okay. But we just randomly assign these, okay? And then we ask R, calculate the mean of all the black dots, calculate the mean of all the red dots, calculate the mean of all the green dots, okay? All right, and so when it does that, okay, we're going to calculate the means of all of these groups, and this is where they end up, okay? The mean of the black dots just by coincidence happens to be here, which I guess that makes sense, just randomly looking at these random assignments, there's a few more black dots over here than there are over here or something, okay? So that's what we get. The mean of all of the red dots is right here, and the mean of all the green dots is right here. So, you know, because it's random, we would have expected the 3 means to be very close to each other, and as far as red and green, they are very close to each other, but the black ones, it doesn't even matter, okay? And then we're going to go through, all right, we're going to go through and we're going to reassign every single dot to the nearest centroid. Okay, so for all of these dots over here, what's the nearest centroid?
Black.
Black, right? Okay, and for all the dots over here, what's the nearest centroid? Green. Okay, and then what about? So if we look at these points here, okay, we're basically going to have to draw like a line halfway between the black and red dot, okay, and then the ones on this side of the line. So let's say I can actually draw, right? So I can I'm going to just draw something like this. And if it's basically on this side, it's going to go into, it's going to say black is the closest, right? And then I got to draw like a line between, I don't know why that happened there. Okay, but a red and a green thing, okay? And basically everything over here will say green is the closest. And then red is only going to get a tiny little sliver right there, okay? Yes?
Random question. What happens if there are no points assigned to a particular centroid in a particular iteration in the process?
Yeah. Then that centroid poof is gone.
Okay.
Yeah. If for some reason in your random process no point gets assigned to a centroid, it gets lost.
You end up with like one fewer cluster.
Yeah. That's what's gonna happen. It could. It could happen. It sometimes happens, but it's not frequently. Yeah. Okay. So we'll do this, and we tell R assign the points to the nearest centroid. Okay, and that's exactly what we get. Okay, we got all of these are assigned to the black, all of these are assigned to green, and only this slice gets red. Okay. And now we say, all right, what is the mean of all the points assigned to black? Okay, it's probably going to be somewhere, I don't know, around here. That'd be my guess. What's the mean of everything that's in green? Probably somewhere around here. I don't know. These are just guesses, okay? And the mean of all the red dots, probably, I don't know, something like that, right? So we're going to recalculate the centroids based on where the dots are. Okay, something like that. All right, so let's see how good my guesses are. Okay, not. Okay, so I was off by black, but the green was pretty good. Okay, green and red were pretty good. I was off for the black. Okay, so we do this, and now we recalculated the centroids, and now we're going to reassign all the points. We're going to say, okay, which dots are closest to the black? So we're going to look basically between black and red. We're going to kind of draw a line halfway in between there, and halfway in between red and green, something like that. And we're going to say all of these are closest to green, all of these are closest to red, all of these are closest to black. Okay, and then and so we do that. Okay, and I think that was pretty good this time. Okay, and then now we recalculate the centroids. So we reassign the points, and now we recalculate the centroids. And I don't know, so probably something around there. Probably we're just going to stay put, and that'll probably go right there. All right, and then we reassign points again. So probably halfway between black and red, something like that. Halfway between, I don't know where this is going, right? So somewhere halfway between red and green, and then so we reassign the points. We recalculate the centroids. We reassign the points. Okay, and at this point, nothing changes. Okay. So after we recalculate the centroids and we reassign the points, there's no changes. So we say we have converged at this point. Okay, and you can kind of compare. This is what we got after k-means clustering. The original data we had a few points that kind of stood out, and of course the k-means clustering has no idea where it started. It just said look for three things. Okay. So this was kind of my manual process of reassigning, like finding the means, reassigning, finding the means, reassigning. R is a function called k-means. Yeah, it's really easy. Yeah, you just do k-means, you throw in your data, you say I'm looking for 3 clusters, and then you store that as the result, and then you can say where are my clusters, and boom, there you go. Okay, it's the same results there. So it just shows you the results after running the k-means clustering. Okay, and here it just kind of arbitrarily goes through and says, these get to cluster 2. These are cluster 1, and these are cluster 3. And these are the means that it has found for each cluster. It gives you this measure of basically the within cluster sum of squares versus kind of the total sum of squares. So the idea is when you've done clustering, you have kind of minimized the within cluster variance and maximized the between cluster variance. Okay. So here we say the between versus the total is around 86.2%. That gets calculated. That's versus like the total variance is like the sum of squares from just the mean of all the dots versus the kind of your. So if I go here, the unexplained variation within is basically the distance from every dot to its centroid, right? So so there's still some quote unexplained variation, and you got to calculate all of these distances squared, right? And then all of these distances squared from every single dot inside here, and then all of these ones, okay? And then and you compare that to no clusters, you'd find the mean of all the points, which is probably right around here in the middle, and you would find the total. You'd have to say like the distance from here, every single dot. Find the total sum of squares, total to the centroid of everything. Okay, and then ideally when you split it up that way, your within clusters is a lot smaller than the total on everything. Okay, and so R will calculate that. All right, this is just kind of what would happen if you use different clusters. Okay, so here I said K is 2. This is the result of having 2 clusters. Here I said let's try looking for 4 clusters. Okay, and this is what it did. Okay, so it's got a green one, a red one, it put a black one here, and a blue one here. Okay, if I ran it with just like a different run using K equals 4 clusters, you can get different results here. Okay, we have black and then red, and then this one gets split. Okay, and it just kind of depends on the initial random assignment. So depending on the initial random assignments in the beginning, you can end up with kind of different end results. Okay. All right, and so here, what I'm doing is I say I've run a loop inside a loop. Okay, this is generally not a good idea, but what we're going to do is I'm going to try looking for just 1 cluster, then 2 clusters, then 3 clusters, 4 clusters, 5, all the way up to 10 clusters. Okay, and then every time I do it, I'm going to run it 20 times. So I'm going to say, look for 3 clusters, but do this 20 different times. Look for 4 clusters and do this 20 different times, right? And so here I did 4 clusters and I got this result, 4 clusters and I got this result, okay? And if we look at it, we can look at the total within sum of squares. So the total within sum of squares is going to be the sum of these 4 numbers, okay? And basically, we want this to be as small as possible, the within sum of squares. And so if I add up these 4 numbers, though, on this run, I got this. And on this run, I got something a little bit different. If I add up these 4 numbers, it's a little bit different from these 4 numbers. Okay, so here my between SS is 87.7, and here it's 88.0. So it's, ever so slightly different. And we can imagine we're going to get some variation when we do looking for 5 clusters or 6 clusters or 10 clusters or something like that. Okay, so I go ahead and I run this. So when you have only 1 cluster, the total, this is like, there's no variation, of course. This was actually kind of stupid. But so we get the same number, 4,462 every single time. With 2 clusters, that drops down to 1,356. So that reduction for K equals 2, 1,356 out of 40, 4,400 is, is only about 30%. So the reduction is, about 70% there. Okay. And anyway, so at 9 and 10 clusters, we can see with 10 clusters, we get fairly different values every single time. 227, 254, 229, 268, 240, 250, 213, 244, 228, 244. So twice we got kind of the same result here. And here is kind of the plot of the different sum of squares values we get, okay? And so we can see with 1, we have this much. Just by adding a second cluster, it drops down. And when I add a third, it drops down even more. And every time I add more clusters, of course, the total sum of squares with leftover variation gets reduced, okay? But we can see that the gains from 3 to 4 and 4 to 5 and so on and so forth is much smaller, okay? And then when you have 10 clusters, you actually get some unusual observations and stuff, right? So sometimes the clustering ends up a little bit off. Is that all right? So that's that is k-means clustering. Okay. Let's save any of these changes. Okay. Did we have any questions on k-means clustering?
When the dots were reassigned to the centroid, do we use the kind of like a KNN method, but it's the one nearest thing to separate?
You assign the dot to the nearest centroid. So you have if you have k-means, you're going to have 3 k different centroids. So if you have 3 clusters, you got 3 different centroids, and you say which centroid is the closest.
Yes.
And wait, so I'm sorry, what's your question?
No, I'm just tying back to the KNN.
There's the similarity between KNN and k-means is just that distance is measured, similarity is measured by Euclidean distance.
Yes. Oh.
But that's it, okay? So, k-means clustering, you're measuring, you're using Euclidean distance to figure out what's the nearest, okay? And k-nearest neighbors, you're using Euclidean distance for what's the nearest. But again, k-means is unsupervised, and you're just kind of searching for, looking for some clusters here. But again, with and this is just in 2 dimensions, but it could work in higher dimensional space. I want to be able to graph it, right? Or it'd be really tricky too.
In higher dimension, is this still called a Euclidean?
Yeah, it's still Euclidean distance. It's just this first dimension squared plus second dimension squared plus third dimension squared, fourth dimension squared. You add them all up and you take the square root. Okay. Yeah. Yes.
At the graph showing the gains, what was that towards the very a k equals 2?
Right here?
Yeah, like that weird. Yeah, what is that?
That's just okay. So we would expect so this is the within sum of squares. So when you run k-n, okay, k-means, okay, when you run k-means in R, it spits back a whole bunch of results, okay? It spits back your between sum of squares, your within sum of squares, and basically the leftover variation is the within sum of squares. It's kind of you can think of it as like ANOVA. So in ANOVA you have your total sum of squares, and then you have except this is like a higher dimensional ANOVA type of thing, but you have your total sum of squares, And then you're splitting that into kind of between the groups and within the groups, right? And the within the groups might also just be called your residual sum of squares, okay? And so the within sum of squares is just going to be the sum of the square distances inside a cluster, right? And so generally that number will keep going down every time you add more and more clusters to search for, okay? And so when I ran this, I just said, do 20 different runs when k is equal to 10, okay? And when k equals 10, I ran this 20 times and I got like the results ended up like slightly different every single time, okay? And most of the time, my within sum of squares was 227, 254, but I did get a result where the sum of squares was 313 and another result where the sum of squares was 309. And apparently, when I make a box plot of these results, R thought that one observation was a bit of an outlier. And so it identifies outliers with these little circles. That's all. It's kind of hard to tell because the fact that this one's up at 4,000 just kind of squashes everything. I probably could have redrawn this to just kind of focus in on 1,500 and less. But I mean, the big thing is that there's a huge reduction in kind of the residual sum of squares or within sum of squares when we go from 1 to 2 to 3, but then how much more we get when we go to 4, 5, 6 to 10 is a lot smaller. Okay.
But if it's like not as much as the first two, should we just choose one with less clusters, or should we just keep going until?
Yeah. So how many clusters? It's an impossible question to answer. Really, it really is. Like for example, okay. So like the census is coming up, right? And then there's going to be a thing, optional question to like what is your race or ethnicity, right? So how many ethnic categories should be on the census? And I don't know how to answer that question, right? So if you say like, okay, how many races exist in the world? It's like impossible. Okay, you can say like, okay, there's white people and not white. Okay, that's one way to do it, right? And that would be 2. Okay, or and depending on where you are, you'd say white, black, or of African descent, and something else, or you can say, okay, well maybe we'll have Asians or also Hispanic, Latino, or something, Latinx. And then, but okay, so you say, okay, we have this many, and then even among Asian people, you can say, well, maybe we should further split that into South Asian and East Asian and Southeast Asian, even like Central Asian. And then let's say you have East Asian, you can further split that into, Chinese and Korean and Japanese. And you can take any of these things and say, well, the goal is to so that the people within the group are different from the people in other groups. And you can always say like, well, why don't we just add another group? So, and it's an impossible thing to say at this point. The variations we're discovering is not important, okay? Like at some point you have to say, okay, well, because every time you add a group, you're gonna reduce your within sum of squares, but it's difficult, right? And so I don't know. I don't know how you should how to determine how many clusters you should have. It's very, very challenging, and it's similar to kind of the impossible question of how many races and ethnicities are there, and yeah.
Yeah, but how do I explain to people like, what do people ask why you choose 3 not 4? Should I say, oh, because
Yeah, exactly. So, well, I mean, you can say adding a fourth, searching for a fourth cluster, did not produce significant, improvement. You can also say, whenever I searched for 3 clusters, I consistently got the same 3 clusters, whereas when I started searching for 4 clusters, it was no longer stable or consistent. That's a possibility as well. But it's hard to, right? Like if you tell people, right, you get to have 6 racial or ethnic groups on a piece of paper, and you give it to 2 different people, they might write down how they split it up into 6. It might be different, okay? And some people might say, I should have split it this way, and then others will say like, no, I don't know. It's hard. So, yeah, we kind of.
Can you just say like anything after 3, just splitting hairs at that point? Like you're making a distinction where there really isn't that big a distinction.
Okay, so I mean the question is the green group different from the blue group?
Very different x2 values.
Huh?
Different.
Yeah, I mean, so the answer is like, yeah, they're different. But then so this is one way to find four clusters here, okay, and this is also another way of finding 4 clusters, okay, and both of these these have reached quote stability in terms of if you calculate the centroids of these 4 and you reassign based on the nearest centroid, no points will get reassigned, okay? And if you do it here and you find the centroids here and you say which one's the closest centroid, no points are going to get reassigned, okay? Is this more correct than this? I don't know. And, is this more correct than this, right? So it's I don't know how to answer this question. And I don't know if we should say we're splitting hairs or not. I mean, so the data was generated using 3 clusters, and so we kind of know the answer and we feel like there should be 3, but at the same time, the thing has said these points are different from these points, and it's hard to argue against that as well. And someone could say, we can just categorize the Chinese people and the Japanese people together, or somebody might object to that, right? And so I don't know, right? So and that's basically what we're doing, right? There's no real labeled structure in the data, right? It's unsupervised, and so somebody's got to kind of make some judgments along the way and say, yeah, these data points seem similar, we can cluster them together, these ones aren't, right? And then there's a huge problem in that we're using Euclidean distance, which is nice for simple toy examples, but in real data, you'll probably have different units being measured, and so if you're measuring people's heights in inches and their weights in pounds and something else, do you then scale them all into z-scores, or do you leave them as is and you do Euclidean distance based on that? There's a lot of questions in terms of pre-processing. So here, these numbers had no inherent meaning. They were all just kind of on the same scale anyway. But you know, there's a question like, okay, do I turn everything into z-scores first and then perform k-means? Do I scale them in some other way, or do I leave them as is, right? And then your question depends on how, like, what units you used, and if somebody used millimeters, those numbers will be like way bigger than if somebody used centimeters, right? So, and that's going to play into part in Euclidean distance. So, okay. All right, that's k-means. That's k-means clustering. I'm tempted to talk about the EM algorithm, but I think we'll just not do it, right? Or do you want to hear the EM algorithm? You do. Okay. All right, well, we'll see how much time we have for the PCA. Okay, so the EM algorithm, so I teach like a machine learning course for the undergrad students as well, and so this is kind of just like some of the lectures that they get. Okay, so here, let me just copy this. Actually, I don't think I want that. Okay, so EM algorithm. All right, so we'll do clustering, EM, and PCA. Oh, I hope we have enough time for PCA still. Okay, okay. So I'm going to start off by just talking about Gaussian mixtures. Okay, and so this is some silly example data where I have mixed 3 Gaussian distributions together, okay? The 3 Gaussian distributions, one is centered at 0, 0, one is centered at 4, 4, and the other one's centered at -4, -4, okay? The one centered at 0, 0 will make up 50% of my values. The one centered at 4, 4 makes up 30% of my values, and the one centered at -4, -4 will make up 20% of my values, okay? The one centered at 0, 0 has sigma matrix 9, 0, 0, 9, okay? So that is that the sigma matrix equals 9, 0, 0, 9, okay? Meaning we have large variance and no covariance, okay? This one has matrix 1, 0.9, 0.9, and 1, okay? So this one will look like a big circle. This one will look like there's high covariance, so it's going to be like whatever that is, okay? An ellipse, okay? It's gonna be an ellipse, all right? And this one has negative covariance, okay? This one is 2, -1, -1, and 2, and it's gonna look like this, okay? And this is centered at -4, -4, 4, 4, and 0, 0, okay? And so when I plot all of this, this is what I get, okay? And so the original data is probably this, and something like this, centered at 0, 0, -4, -4, and 4, 4, something like that, okay? But you don't know that, okay? You don't know that. And so when we look at this, there's a question, all right, let's look at this data point right here. Is this data point part of this thing, or is it part of this thing, right? We don't know, okay? And the answer is it doesn't matter, okay? We don't know, all right? The EM algorithm is kind of a cross between the Bayes classifier, right? So you guys are all familiar with the Bayes classifier because you've been doing it in your homework, right? And so the Bayes classifier, how do we categorize the Bayes classifier? How does that work? So here, basically, this dot, we have two competing probability things, right? So this dot, we're going to say can be, if I call this one A and this one B, and this one C, okay? So the Bayes classifier is going to say the probability that it's A, given basically the data and current estimates, is going to be equal to basically the probability of this point. What is this point? Negative 8, 0. Okay, we're going to say negative 8, 0. The probability of getting negative 8, 0, if it were class A, times the probability of being in class A, divided by, I'm just going to write the marginal. Okay, and then the other kind of computing thing would be what's the probability that's going to be in class C, given the data and current estimates. And this is going to be, okay, well, what's the probability that this thing produces the value negative 8, 0 if it comes from class C, times the probability of coming from class C, divided by the margin, all right? So so it's like the Bayes classifier, all right? Except, here's the thing. So the Bayes classifier is a supervised thing. You know every point in the training data is already labeled, and so you know from your training data, these ones are from class A, and these ones are from class B, and these ones are from class C, and therefore I have an estimate of what the mean of class A is, I have an estimate of what the mean of class B is, I have an estimate of what the mean of class C is, right? So in your homework you can say, because I know these ones are setosa, I know that the mean sepal length is this, and the mean sepal width is this, and the blah, 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 okay? And because all of these other ones are virginica, these are my estimates for this, okay? The EM algorithm for Gaussian mixtures is unsupervised, okay? We can use the Bayes classifier, except we don't know the true assignment of any of these points. We don't know which one of these points belong to class A, which ones belong to class B, and which ones belong to class C, okay? So what we do is every point gets a probabilistic assignment, okay? So the output of the Bayes classifier is a vector of probabilities. It says it's class A with probability 0.1, class B with probability 0.8, class C with probability whatever's left over, okay? And we do that every single point, okay? And then, so all the points have like a probability of belonging to class A, right? So then, and a probability of belonging to class B, and a probability of belonging to class C. So what is the mean of class A? The mean of class A is going to be the weighted mean of all of your data points, and it's weighted based on their probability of belonging to class A, okay? So the points that have a 99% probability of belonging to class A, basically they count their full weight, okay, as far as calculating the mean. And then this point over here, which is, way over here, whatever, maybe it only has a 1% probability of being in class A, okay? So then it only contributes 0.01 to calculating the mean, okay? And so it's kind of so it's like a k-means and the Bayes classifier, right? And so it's iterative in that we will recalculate the mean of A and the variance of A and the mean of B and the variance of B and the mean of C and variance of C. At every single iteration based on kind of these weighted probabilities. And then after we do that, we reclassify using the Bayes classifier. Using the Bayes classifier, we give everything a probabilistic assignment. After we've done the probabilistic assignments, we recalculate our estimated means and variances of each class or cluster, and then we reassign or we classify to the clusters probabilistically using Bayes classifier. Does that kind of make sense, what's happening? So it's like k-means in that it's iterative, except k-means is just like this one's the closest, so you're definitely this, and this one's the closest, so you're definitely there, okay? Here, we're being a little bit more loose. We're gonna say this one seems more like it's more probable that you're here and less probable that you're on this one, okay? And then when we say, okay, well, what's the mean, is we say, all right, we're gonna take the average, the weighted average of these things, okay? So these are the true mixing things, and you know, we just say, you know, like, where does this point go? It could be in the red cluster or the black cluster, but we're not quite sure, okay? And so we're gonna do some kind of probabilistic thing, and that's what we call, okay? So the EM algorithm is, we use the Bayes classifier for a probabilistic assignment. We call that the membership weight. That's the E step, okay? And then once we have the membership weights, we calculate the parameters of the cluster. We get the kind of the weighted mean and the weighted variance covariance matrix, okay? To try to, you know, figure out what these things should be, okay? And so recalculating the parameters of the cluster distributions, that's the M steps. That's the E and the M. E is the expectation and M is maximization. We're trying to just find the expected membership weights and maximize the maximize the likelihood of our data using the parameter cluster distributions here, okay? All right, so this is just fancy speak for it's just the Bayes classifier, right? So the likelihood is, what's the probability of getting this X if you know that, you know, given this kind of assignment and the means that it belongs to, the mean and variance of each of the clusters, okay? Times the prior probabilities, which we are going to store in alpha, okay? I'll post all of my notes here. All right, so the alpha, this prior, is basically how many points belong, like the proportion of points that belong to a certain cluster, right? So like when we generated this, we said like 30% belong to, you know, this cluster and, you know, 20% belong. So something like that, okay? Except right now, we don't actually know which points belong where, right? And so what we're gonna do is we're gonna just have we're gonna have probabilistic weights, right? So our, so, you know, we have observation 1, observation 2, observation 3, and 4, and so on and so forth. And we're going to say it's cluster A with 0.5, cluster B with 0.3, and cluster C with 0.2. Observation 2 is cluster A with 0.1. This is maybe 0.8 and 0.1, and this is, you know, 0.1, 0.7, 0.2, and this is 0.8, 0.05, and 0.05, or something like that, okay? And so currently, how many points belong to cluster A? It's going to be the sum of these things. So none of these points truly belong to cluster A, but if we had to get an estimate of how many points are in cluster A, it would be 0.8 plus 0.1 plus 0.1 plus 0.5, and we would have 1.5 points belong to A. And then we would add how many belong to B. What's that? 0.15, 1.85. And then here we would get 0.55 or something like that. Okay? Yeah.
So in this case, should it be for cluster 4 0.8, 0.1, 0.1, or do they?
Oh yeah, yeah, they should add up to 1. I'm sorry. I'm silly. Okay, so yes, thank you. 0.1, 0.1, so this is 1.9 and this is 0.6, I believe. Okay, and yeah, and if we add those up, there's a total of 4 points, okay? But 1.5 belong to A, 1.9 belong to B, and 0.6 belong to C. All right, so that's going to be kind of like your prior probabilities, the alpha sub k. Does that kind of make sense? So it's a little bit weird because there's not like real assignments, it's all just probabilistic assignments, yeah? And then, okay, yeah, this is a mess here again. Okay, so now we're going to just say, okay, well, what's the likelihood? The likelihood. So the likelihood is just going to be your density, okay? And now we just use the multivariate density, which we can, thankfully, R can do this nice and easy for us using the density of the multivariate normal, right? You give it some vector of the value that you have and the current estimated x bar sub k and the current estimated variance of cluster k. So this will say, you know, for basically, you know, you have for the center cluster, like you have a very high probability, the density is high in the middle and it's lower as you go out, okay? And over here, the density is the highest for this cluster and it's lower as you go out, and it's like 0 way out here, right? Okay, so you figure out your the density of the multivariate normal, okay? And then the marginal is just the sum of the numerators across everything, right? So, you know, we probably don't even have to worry about that. So we just multiply the densities times the prior probabilities, and then we're going to divide by the marginal, which is just the sum of the numerators. Okay, and so the other part is how do we get the means? Okay, and this is just the weighted mean. So we take each membership weight and we multiply it by the x values to kind of get a weighted mean, a weighted average. Okay, and then we also do a weighted variance covariance matrix. Okay, so the variance, the regular variance just doesn't have this W thing, right? You do x minus mu times x minus mu transpose summed up, okay? That's kind of a variance, like a multivariate variance covariance thing, okay? This, we're just gonna take each thing and weight them with a W. Right, and so that gives us our estimates of each variance covariance term. Is that okay? All right, and so this is just kind of an illustration of how it works. This is not an accurate illustration because, so I'm going to color the dots, but the coloring is wrong, or is maybe misleading. Okay, I wouldn't say wrong, but it's misleading because the coloring gives the impression that the dot belongs to one cluster. But the dots don't actually ever belong to one cluster. They just have probabilistic assignments, okay? So it's going to be like, this dot is 80% A, 10% B, and 10% C, but it's going to get colored in the picture as being in cluster A, okay? Because I'm just doing kind of which one has the highest probability, and it's going to be colored as such, but none of the dots are truly 100% cluster A or cluster B or cluster C. It's just going to be, you know, if this dot is 60% C and 30% B and 10% whatever, it's going to get colored as cluster C because it's 60% cluster C. Yeah.
What if there is a tie?
What if there's a tie? Okay, I mean, it could happen, but the ties only make a difference as far as the coloring goes. Okay, but it doesn't even matter. Even if there's a tie, it all just gets handled here with the W's, okay? As far as the coloring goes, I don't know if I experienced any ties. I just did ask R to color it based on the maximum probability, the resulting probability. So again, you know, it might be misleading. But the ties don't even matter because they're just membership weights, and you just weight them as to figure out your estimate of the mean and the variance, and then you recalculate your base probabilities as well. Okay, so anyway, these are the true groups, and so here I just started off with 3 kind of arbitrary starting things. I just said I'm going to start off at 0, 0, -9, and -9 and 9, 9. So these are kind of the centroids. Here's centroid 1, centroid, or I guess mean 1, mean 2, and mean 3, and I gave all 3 of them the same covariance matrix. Okay, So these are definitely wrong, okay? So we just start off with some initial means and initial covariance matrices, okay? And so basically, you know, I've got basically a normal distribution centered here, a normal distribution centered here, and a normal distribution centered here, okay? And so based on this, we end up getting like these dots right here are equally likely to be in this one as they are to be in this one, and that's why we get kind of this drawing here. So it's just at this point they do this. Okay, so again, none of these points are truly assigned to here. These are like 51% this one and 49% the center, and these ones are over here are 51% here and 49% to that one. Okay, but based on all of those kind of probabilistic assignments, we recalculate. Okay, so again, this is misleading. We recalculate where the centroids, not the centroids, but we recalculate where the means are. These are the weighted means and the weighted variances of these things. Okay, so I do this, and I'm going to just show how the coloring kind of goes. All right, so after running the algorithm, it's kind of I don't know why I keep saying one iteration. Okay, so several iterations, and it kind of eventually this is where it converges here. Okay, and it seems like it has recovered the original kind of clusters fairly well, right? And again, these are just probabilistic. So these probably ones on the boundary are like 50%, 51% black, 49% green, and this one's 51% green and 49% black. Type of that, okay? And so we have these probabilistic assignments, and it does that. So with each iteration, it just recalculates its probabilistic assignments using the Bayes classifier, which gives us probabilities of each class or cluster, and then it recalculates what the mean and variance are for each one. Okay, and these were the true groups. So the coloring is completely arbitrary. Like, it just says this is one and this one. So this one says ended up red and this one ended up green, and you know it doesn't matter. Okay, so you know here basically everything here is going to be like has a higher probability of being in the red, even though it's truly like a mix of this cluster and this cluster. Okay, but the EM just says everything in here basically has a higher probability of being in one or the other. If you start off with some bad initial weights, you can end up getting the wrong thing. So here I start off with some different starting locations. So I'm going to just say this is the first cluster and this was the second one, and I run this, and after many iterations, this is what it gets. But it ended up being kind of stable. Like this thing ended up being stable on its own out here. Okay, so sometimes you can end up with like the wrong thing as well. Okay, so the EM algorithm. So this one just ended up kind of stable over here, whereas as far as the other one went, like it pretty much got it right over here. Okay, so that's k-means clustering, and then which uses hard assignments using Euclidean distance. Whichever one's the closest, it assigns it to that. And then the EM algorithm uses probabilistic quote assignments, probabilistic membership weights. Okay, why don't we'll take a 10-minute break here, and then we'll take a look at PCA afterwards.